Okay, but let's get going on our last chapter of the semester, your last chapter before your next test and before the midterm. Chapter 8. Chapter 8, we're going to introduce our last postulate of geometry, the parallel postulate. So chapter 8, all about parallel lines and things we can start easily proving once we have parallel lines. So first off, what does it mean for two lines to be parallel? If I know that this line was parallel to this line, what does that mean?
They don't intersect.
They don't intersect. That's our basic definition for a parallel line. So lines L and M are parallel if and only if they don't intersect. We use this notation, L is parallel to M. And that's a quick way of denoting it. The same way we already introduced a notation like this, L is perpendicular to M. And then I have L is parallel to M. So two common pieces of notation that we have. Okay, now a definition for two rays pointing in the same direction. Now what does it mean for two rays to point in the same direction? Are these two rays pointing in the same direction? No. Are these two rays pointing in the same direction? This one and this one? Roughly, based on my picture? Yeah. Are these two rays pointing in the same direction? This one and this one? No. So what does it mean for two rays to point in the same direction?
The lines on them are parallel.
So first off, the lines through the rays have to be parallel. That's what we'll mean by the rays are parallel. The rays have to be parallel, and what else?
They have to lie on.
Because notice this and this are parallel.
Right.
So how else? What else do they have to be?
They have to be on the same side of the.
Yeah, the two rays have to be on the same side of a line that goes through their vertices. If I draw a line through these two rays' vertices, then they'd both be on the same side. If I drew a line through these two rays' vertices, the rays now are on opposite sides of that line. So, two rays have the same direction if and only if they are parallel and lie on the same side of the line through their vertices. Picture roughly like that. Make sense? Okay, now we're going to get our first theorem that we're going to prove, kind of an interesting one. We're going to prove that if I were to give you a line L and a point A, there exists some line through A parallel to L. That's what we're going to try and prove.
Wasn't that Euclid's fifth?
No. Euclid's fifth, we'll introduce Euclid's fifth, but it's going to be logically equivalent to there's only one line. So first I'm going to prove that there is a line through A parallel to L. And then we'll bring up the question of, is it the only line? But let's start with just proving one. How is this picture going to go roughly? First thing I'm going to do is I'm going to pick some point B down here on L. I think I'll call it B. And then we're going to create some line L prime through A and B. Right? I know there's at least one point on L. Call it B. Now I have A and B. That gives me a line L like that. Now, notice that we have an angle here, right? And I know that at a point, if you give me a point and a ray, think about the half from here outwards as a ray, then there exists one and only one ray I can construct on a given side, such that my angle will be congruent to this angle. So there's one and only one ray I can now come stick along right here. I think I'll call it R in our proof. Such that this angle now is congruent to this angle. You get me?
Yeah.
Now draw the line across through that ray, and I think I'll end up calling it line M in our proof over there. And now how do I know that these two lines are parallel? What's our definition of two lines being parallel? They don't intersect. So we're going to assume by way of contradiction that if you fill these out far enough, then they do eventually intersect at some point C. Impossible picture. We're going to prove that's an impossible picture. It's impossible for these lines to eventually intersect. What would happen if they did intersect?
It will create a triangle.
ABC is now a triangle. You see that?
Yeah.
And now notice, how does this angle compare to this angle?
Exterior.
It'd be great.
It's an exterior angle, and they're the same size. What have we already proven?
The exterior angles have to be bigger.
An exterior angle is always larger than either of its opposite interior angles. Contradiction. So this picture is impossible. That's big picture flow. Let's walk through the nitty-gritty. So if A is a point not on line L, then there exists a line through A parallel to line L. Exactly what we're going to prove. So how did we start? Let B on L be some point on L, and let L prime be some line through AB. Let R be a ray from A such that angle A is congruent to angle B. Good? It doesn't matter if we were talking about going this way or if we were talking about going this way using this angle. Same picture, just on that side. So the sides here don't matter which way we're going. Assume by way of contradiction that L intersected M at some point C. So you extend the lines long enough, they eventually intersect at some point C. Then we have that angle A is exterior to triangle ABC. And we also have angle A is congruent to its opposite interior angle. Contradiction. Therefore, line L must be parallel to line M. They can't intersect. There's the proof. Good? Any questions so far? Okay. So now we introduce our last postulate of the course, and that is the parallel postulate. What's the parallel postulate? If A is a point not on the line L, then there exists one and only one line M through A such that M is parallel to L.
Why is that?
So we prove that there's at least one line, and as our postulate is, and there is only one line. And now, why on earth would we have to have that as a postulate? Why would I have to have, if I've got some line L here, some point A, isn't it obvious that there's only one line I can draw through A parallel to L?
Yeah.
Right?
Because
Because if we were to somehow slant a little bit off of this line, if we call this line M, if we were to somehow slant a little bit off of it, then we'd eventually intersect on that side, right? So why do we have to have this as a postulate? Maybe there's some clever way to prove this from what we've already been given. And we don't need it as a new postulate, and somehow it can be proven. And that is a very tempting thought. And a lot of very, very smart people spent a ton of time, 2,000 years, trying to do that very thing. And the conclusion, shockingly enough, is that it's not possible to prove it, and you do have to have it as a postulate. Which means that there exists some other geometry out there where it is possible to have more than one line through the point A parallel to line L. Now, how does that make any sense? And so, we're going to talk a little bit about what are called non-Euclidean geometries. We are in a class today called Euclidean geometry. And so, I've already given you the postulate that we're interested in. I'm going to introduce you to different geometries based off of different postulates. The first non-Euclidean geometry to be developed was called hyperbolic geometry. This was a geometry that has, up till now, everything identical with our geometry. Nothing different. The only difference is, rather than they're saying that there's one and only one parallel line, their postulate would be, and there's more than one parallel line. And that would be the only difference. So to give you the structure of thought so far, we've had logic. On top of that, we built set theory. Here's what we've built from our class so far, our geometry. And for now, here we need to make a choice which postulate we're going to use. If we're going to use this postulate, we're developing what's called Euclidean geometry. If we were to pick the one that says there's more than one line, we'd be developing hyperbolic geometry. And that's the difference between those two. The final one is called elliptical geometry. Intuition, what is the difference between these three geometries? There's way more than these three, but these are the three common ones that people talk about. What is the difference here? Euclidean geometry is a geometry you're doing on a flat surface. Hyperbolic geometry is geometry on a hyperbolic surface. The intuition we often get for that is like on the surface of a saddle.
I was going to ask what hyperbolic means. I don't like what the origin is, why it's named differently.
Its curvature is like that of a parabola, or of a hyperbola. But doesn't matter. For now, we'll just keep it as a name. And then finally, elliptical geometry would be geometry like on the surface of the Earth. So you have that kind of curvature. It curves in on itself. Hyperbolic geometry, it curves outwards, expanding forever. Euclidean geometry, it's flat. elliptical geometry, that's one that's kind of easy to get more intuition for than hyperbolic geometry, so we'll talk about this one for a second. But this one, we'd have to have much different postulates than what we've used so far. So in hyperbolic geometry, imagine we were doing geometry on the surface of the Earth. First off, a line, in that case, would be what on the Earth we call a great circle. So the equator would be a line on the surface of the Earth. And then this line of longitude that goes up around the North Pole and back would also be a line. And notice something. How many times does the equator intersect this line that goes through the North and South Pole? Twice. In our geometry, two lines can never intersect at 2 points. In elliptical geometry, any two lines intersect at 2 points.
Yeah.
The lines of latitude here, with the exception of the equator, aren't lines in that geometry, they're curves. The only line of latitude that is an actual line in that geometry is the equator.
Yeah.
The rest of them aren't lines. They're curves in that geometry.
Why?
Huh?
Why?
Because one of the notions we want is that the shortest distance between 2 points is along a line. And the lines of latitude here are not going to give you your shortest distance between 2 points. And so if you were to look on a map, for example, about the flight an airplane takes between two cities, an airplane does not care about going straight as it shows up on a map. They're just trying to minimize the amount of fuel they use. So they're just looking for the shortest path. And so if you looked at it on some picture, some flat map of how they were moving, then you see that they start here, and if they end here, you're going to notice that their path looks something like this on a flat map. And that's going to correspond to, on the Earth, they took a straight line on the surface of the Earth, but when you project it onto a flat map, it looks curved. And so in elliptical geometry, here is straight. And your line of longitude might look straight on the flat map, but it's actually going to be a curve on the surface. So not at all. It's hard to get your intuitions good for these things.
Why is the equator a line and not any?
So if you were to pick any 2 points on the surface of the Earth and plot the path that connects those 2 points, and then keep making the path all the way around the circle, it turns out that that path is going to be along a diameter. So pick any 2 points, find the shortest path between them. The shortest path between them, if we were to create that line indefinitely, it would circle all the way around and it would perfectly be along a diameter of the Earth every time. The equator is the only line of latitude that goes around the entire Earth. Right? This line of latitude right here does not go around the entire Earth.
Okay.
But all your lines of longitude would actually be lines. Because they all go completely around the entire circumference of the Earth. So that's a little bit about elliptical geometry. Hyperbolic geometry, which was the first of these geometries to be discovered, is the one that intuitively, it's the intuition we use, it's geometry we would do on a horse's saddle. That's roughly the intuition that we get. Now, another property that our lines happen to have in our space, our parallel lines, is if these two lines are parallel, then the distance from here to here and the distance from here to here are the same. So that's one of the ways someone thought that they were able to prove this postulate. They said, well, parallel lines have to maintain distances between them the same. And so, this is the one and only one line that does that, which happens to be true, but they're just giving a logically equivalent one. So let's jump into hyperbolic geometry here for a second, give you some intuition for it. So here I'm going to draw here we are in Euclidean geometry. Here's two parallel lines, here's one, here's the other. Here's the point A, B, C, D. Now in Euclidean geometry, that segment is definitely the same long as that segment. You with me? Okay, now new picture. Over here we're looking at some horse's saddle. Except for it expands to infinity everywhere, but typically you use horse's saddle as intuition. Now I draw this line on the horse's saddle. We're looking at the horse's saddle side on. So here's some line I go and I draw on the horse's saddle. And it's got another line on the other side, just as high up on the saddle. We can't see it. You with me? Now, let's think that this is what it looks like from a bird's eye view. Looking down on the saddle, here's this line. And looking down on the saddle, I can see the other line on the other side. Here's the segment connecting the point A that goes around back to the point B. And here's the segment that connects the point C going around to the point D. which segment is longer? This one or that one?
AB.
Right. And so you'll notice those two lines on the horse's saddle are parallel. They'll never intersect each other. So they are parallel. But the distance from A to B is way bigger than the distance from C to D. And so in hyperbolic geometry, parallel lines do not maintain distance between them. And now the horse's saddle is a bit misleading because it's not really a horse's saddle. It keeps expanding like that forever into infinity. And so now imagine that I drew some other line right here that went through the point C and went like that. If this keeps expanding up, my saddle keeps getting taller and taller infinitely, notice that this line is going up the saddle slower than the saddle is getting tall. Will this line ever get over the saddle if the saddle is growing faster than it's rising up?
No.
No. Is this line the same as this line? No. Will it ever get over the saddle? No. So can it ever intersect the line on the other side of the saddle? No. And so it is also parallel. And any line between them is going to be parallel. And so there's an infinite number of parallel lines. So in Euclidean geometry, once I give you a line and a point not on the line, there's one and only one line through that point, parallel to the given line. In hyperbolic geometry, there's an infinite number.
Why does hyperbolic geometry have planes like that, though? That like are like a horse's saddle?
Well, why on earth do we assume that this flat board is a good approximation for the geometry we're talking about? Why does it have to be flat? Why couldn't it have this curvature? How are we justified in saying our surface is in some sense flat? And we've been just assuming that the whole time, that a plane is flat, but how do we know that? And it turns out this parallel postulate, that's one of the things it's saying. Hey, the plane you're in, it's flat. And we have to take that as an assumption. Why couldn't it have any curvature to it? Why couldn't we have been on some curved surface that bends in and out on itself? Why does all our space have to be so nicely uniform? That if two lines go along, then the space between just has to stay the same. It's very intuitive because Euclidean geometry is a fantastic model for the space that we're currently in. And so that appeals to our intuition very much because we occupy a space that's basically Euclidean. But there's no reason that the geometry we're constructing has to have that property. And so the geometry that we use to model the space that we're in, assuming we're not modeling the universe as a whole, but just this local space that we're in, is Euclidean geometry. So we have a bunch of intuition for it.
Yeah.
But if we were doing geometry on the surface of the Earth, for example, things get very different. We're going to prove in our geometry here in a second that the angle sum of any triangle is 180 degrees. A straight angle, or 180 degrees, however you want to say it. Let's imagine making a triangle on the surface of the Earth. So I picked some point. Let's kind of draw it and see it at the same time. I'm going to pick my triangle to be like this. I don't know how good my art is. And then, let's see, what would an equator line look like? Maybe I need to drop this point down to the center. Okay, so I construct a triangle using like this 8 of the globe over here. So here's A, here's B, here's C. You see it?
Yeah.
That would be like, so one of my points is at the top, one of them's perfectly on the equator down here, and then one of them's perfectly going halfway from what you can see. You see it?
Uh-huh.
Now, what is this angle right here? The angle between the equator and going straight up to the North Pole. It's 90 degrees. Those are perpendicular to each other, right? So this is a 90-degree angle. Same with this one, it's the same thing. That's just some other point. Equator going straight up. And this angle at the top, since we're doing 1/4 the circle, so it's coming up like that and then going out like that and coming down, is also a 90-degree angle. What's that angle sum? 270 degrees. And so in elliptical geometry, it is not true that the angle sum of every triangle is 180 degrees. In fact, every triangle's angle sum will be over 180 degrees. really small triangles will get really, really close to 180 degrees, and really big triangles will get close to 270, all the way up to 270 degrees.
So it's not the same across all triangles?
So it's not even the same across all triangles. Because when we draw a triangle on the surface of the Earth right here, it basically adds up perfectly to 180 degrees. On the other hand, when we do it on this scale, it's not even close.
So the curves work?
Yeah. You get more curvature the bigger you draw your triangle, the more it distorts your triangle.
What about hyperbolic geometry?
Hyperbolic geometry, the angle sum. So in elliptical geometry, your triangles, when we draw them roughly like this,
Yeah.
to help us remember. In elliptical geometry, our triangles look like this.
Oh.
And the angle sum is always less than 180 degrees.
Why is it always?
It's the way the curvature is going. It's got inverted curvature. In elliptical geometry, it's curving in on itself, which gives your triangles more space to bend into, and so they can make their angles bigger. Hyperbolic geometry, the bend's the other way, and so it's taking away the space that they had to bend into. I don't know how to give you good intuition for this right on the fly.
Yeah.
But those are the three basic types of geometries.
You mentioned there were more.
Yeah.
Yes.
What other words?
There's no reason that we have to be limited to these geometries. And elliptical geometry is a type of Riemannian geometry.
Riemannian?
Yes.
Like-
It was the mathematician Riemann who first saw Euclidean geometry, obviously Euclid. Hyperbolic geometry, the first person to do that, his name is Carl Friedrich Gauss. He's the first one to develop hyperbolic geometry. Now, he's not the first one to publish. He held off publishing. Do we want the history?
Yes.
We'll do a little bit of the history. So, he was hesitant to publish because there's a famous philosopher by the name of Kant, Immanuel Kant. And Immanuel Kant's philosophy, it kind of has Euclidean geometry baked in as being true. And so it's impossible to have any other type of geometry because this is the geometry. It's kind of built into his philosophy. So Carl Friedrich Gauss comes up with this hyperbolic geometry, and he realizes, no, you can't go around saying Euclidean geometry is true. You can say it's a good model for reality. But that contradicted this philosophy. Now, the name probably means nothing to you today, but Immanuel Kant, he was the intellectual superstar of his day. The Germans absolutely loved this guy. People thought he was an absolute genius.
He was German?
Yeah,
Okay.
he was German. And so, to put out publishing results that contradicted what Kant had already put out there would instantly put you in the spotlight, so to speak. Now, Gauss is about 50 years younger than Immanuel Kant. So by the time Gauss is coming to the scene, Immanuel Kant has already been established and he's a genius, and you just don't argue with Kant. And so he didn't publish. Now, the son of a friend of his, by the name of Bolyai, eventually ended up making a bunch of these discoveries too. And he was excited about the discoveries he was making, and his dad had a connection to the great Gauss. By the time Gauss is coming along, he's recognized as a genius mathematician. So he wants Gauss to look at some of the stuff he's been doing. And Gauss says, yeah, that's great. I've noticed some similar things, but I've already done a bunch of this work myself. That's cool what you're doing. And he was a bit disappointed that Gauss wasn't as excited about his great discoveries as he was. And it also happened that at about the same time, another Russian guy by the name of Lobachevsky made the same discovery. It's so strange how that sometimes happens in history. There's just nothing, 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 and then you get a bunch of breakpoints simultaneously, a bunch of breakthroughs simultaneously.
Yeah.
Like with Leibniz and Newton with calculus, for example. So, they did that with hyperbolic geometry. Now, hyperbolic geometry was in a sense easier because you notice it has a ton of overlap with Euclidean geometry. It's just this one thing you got to tweak.
Yeah.
Elliptical geometry is the first of a Riemannian geometry, and it was the mathematician Riemann who started axiomatizing these new geometries.
He was a while after that, wasn't
When was he?
He is. No, he's not way after. What is the time frame between him and Gauss? It's not 100.
he? Is it?
No. So,
Was Gauss alive when Newton was?
no. Newton's way earlier.
He's
Newton presupposes Kant by good amount. Gauss, Let me think. I think Gauss died in 1855.
Okay.
So I'll give you a sense for how close he was. So his life and Riemann's life definitely overlap a lot. The age gap between them, I don't know.
Is this the same Riemann as Riemann's sons?
Yes. You'll notice with these early mathematicians, their names just pop up everywhere.
Yeah.
You can't get away from Euler. He's everywhere. He did everything. It's nuts. And Gauss is kind of in that same boat, and Riemann's kind of in that same boat.
What's the big difference between elliptical geometry and geography?
And
Like,
what?
Because geography is just also.
Geography is just talking about where things are located relative to each other.
I know, but you're saying it's based off of a globe.
Elliptical geometry is doing geometry on surfaces. The globe is an example, but just on the surface of a circle, on the surface of a
On
sphere.
the sphere. Okay, so it's
Yeah.
like 3D stuff, essentially.
No, it's a two-dimensional surface, right? The surface of the Earth is two dimensionals,
Oh, yeah, okay.
right? The surface of a ball, two dimensionals. The surface of some sort of elliptical shape, you know, some sort of elliptical sphere, take an ellipse and twist it on itself, and the surface it carves out, is two-dimensional. Now, you can't have three-dimensional surfaces. We are in a three-dimensional Euclidean space.
Yeah.
Trying to comprehend a three-dimensional hyperbolic space is so crazy hard to do. Give you an example. If I were to take some ball and throw it at you, you wouldn't even be able to see it until it was like this far away from your face. And it would suddenly go from a small dot really big. Because it shrinks, the space grows so fast, you're seeing so much space. And so, the object it only looks as big as the amount of space it occupies relative to everything you're seeing. And so if you're seeing all that, since space is growing so much, massive objects are taking up less of the space you can see. And so an object that's a foot away might look like in our geometry, it's 100 feet away. Because we're seeing the same amount of space. What we might see in 100 feet is what, if we were in elliptical geometry, you might see in 1 foot, in terms of how fast the space grows. So it's very hard to get intuition for what these types of things would be like. So you could do it 2 dimensions, you could do it 3 dimensions, you could do it 4 dimensions, but when they were first being discovered, they were just doing it on 2-dimensional surfaces. 2-dimensional flat surface, 2-dimensional surface that curves away from itself, 2-dimensional surface that curves in on itself.
So what did Riemann do when he was doing this?
So he axiomatized these elliptical geometry, but then there's other geometries that we call Riemannian geometries that don't have necessarily uniform curvature. And now you might start thinking about surface of manifolds, for example. After manifolds, a natural field to continue into would be Riemannian geometries. Sorry.
Yeah, okay, that makes sense.
But yeah, these systems were much harder to axiommatize because now we got to re-talk about what we mean exactly by a line. Because over here, 2 lines can only intersect at 1 point. Here, every single line intersects at least 2 points.
So
or at 2 points.
the space you're doing elliptical geometry in is somehow finite?
Yes, it's somehow finite. It somehow has to curve back in on itself. Every line extended far enough comes back full circle.
So like it can't, like in other geometries can be infinite though?
That's what we assume in Euclidean geometry. I say, how long is a line? You say it goes on forever. I say, how long's the equator?
60,000
You say 23,000 miles or whatever it is.
Yeah.
Big difference, right?
Yeah.
Anyways, so that's giving you a taste for the different geometries. The geometry that we are in is Euclidean geometry, and so this is the postulate we'll be using. Now, one more point to emphasize here is, should we be able to say which of these geometries is the true geometry? Like, what is it really, though? Is it that there is only one line or that there's more than one line? What's the right answer, really? You can't tell me that there's no right answer. And unfortunately, the answer is there is no right answer. Because remember, in geometry, we never say our postulates are true.
Right.
We say if our postulates are true, then our theorems are true. And you use this thinking all the time in your math class. If I say if 5x plus 4 equals 14, then x equals what? 2. Okay, you figured out x. Now you go on to the next problem in your algebra class, but you already know x equals 2 and you go on your merry way. And now from there on out, every time you solve a math problem, if you see x, you just replace it with 2, right? Because you found out x is 2. No, x is 2 if this is the case. And when you move on to a new problem, we are no longer assuming that this is the case. In Euclidean geometry, we are not saying that the axioms are true. We're saying if the axioms are true, then the theorems are true. We're saying if, then. We are not saying this is the case. And so we look around at this space that we occupy, and the better question is, what geometry models this space? And so that's the point of geometry. We can start validating the axioms in this space. So what are some of our axioms?
In the space?
What are some of the axioms for our Euclidean geometry?
There are at least 3 postulates.
Yeah, there's at least 3 non-collinear points in a plane. Is that true in this space that we occupy? Let's see if I can do it. I did it! Okay, that seems to be true in this space.
Yeah.
What else? If you have 2 points, can you get a line that goes through them?
Yeah.
What else? If you give me a line, can I find 2 points on there? I think I see one right there. Yep. And is it true that in this space, if I draw you a line and give you a point not on the line, that there's one and only one line you can draw through that point such that these 2 lines are parallel?
Yeah.
Yes. And so those of you who remember the different types of reasoning, going all the way back, what would we do? We would inductively validate the postulates, and then from there on out use that geometry to model our space. So we confirm the postulates hold in this space. And then what do we know from our geometry? Our geometry says if the postulates are true, all the theorems you get for free.
Yeah.
So we check, are the postulates true in this space? Then we get all the theorems are true in this space for free. And so once I validate our postulates, I don't even have to go check, does the Pythagorean theorem hold in this space? I know it does.
Yeah.
I don't have to check, is the angle sum of any triangle 180 degrees in this space? I know it is. Because I just have to check my postulates. And if the postulates hold, we're good. If I were to check the postulates of elliptical geometry in this space, we would find that they don't hold. And so this would be a bad model, and this is a good model. Make sense?
Yep.
Okay. So that's our conversation about Euclid's fifth, about the parallel postulate. They often refer to this as Euclid's fifth because it's the last postulate he introduced, and it was his 5th postulate. So the parallel postulate, which it's also called, is also referred to as Euclid's fifth. I may accidentally say that. If I say Euclid's fifth, I mean the parallel postulate, which is that postulate, which is given a line and a point not on the line. There's only one line through the given point, such that the 2 lines do not intersect. Okay, so with all that, let's now do some quick proofs using our parallel postulate. I won't bother writing these out unless you want to see them. First I'll give you the picture, and then if it feels obvious, we'll call it good. If you want me to write it out, I can. So first we're going to prove if L, M, and N are distinct lines such that L is parallel to M and M is parallel to N, then L is parallel to N. So let's draw these out. Here's L, here's M, here's N. I know this is parallel to this, and I know this is parallel to this. I'm trying to prove that this is parallel to this. You with me?
Yeah.
Let's draw my N up here. It doesn't matter what order I draw them in. It'll just keep our picture a little bit cleaner. So I'll put the N up here. So this is parallel this is parallel to this, and this is parallel to this. I'm trying to prove that these 2 lines are parallel to each other. We have, everyone.
Good morning. Okay.
Good morning.
Good job. That's awesome. I still that stuff is so cool on the board. It's like, wow. Thank you.
Thank you. All right. So I'm trying to prove that N is parallel to L. Here's what we're trying to prove right up here. Now, how do I prove this? I'm going to prove it by way of contradiction. Let's assume that N and L actually weren't parallel. If they're not parallel, then what?
They intersect.
They intersect at some point, call it P. Now I know M is parallel to L, and I know M is parallel to N, and these 2 lines go through the point P. How do I know that's impossible?
There's only one.
How many lines do I have parallel to M going through the point P? Is L parallel to M?
Yes.
Is N parallel to M?
Yeah.
Do they both contain the point P?
Yes.
How many lines do I have containing the point P parallel to M?
4.
2.
Oh, 2.
right.
Well, that's a
2.
contradiction. But
How many am I allowed to have? 1. Contradiction, so that's an impossible picture. If these two lines intersected at some point P, then I would have 2 lines through P parallel to N, which is impossible from postulate 6.1. Good? Want to see the proof, or you think you're good?
Proof?
You want to see the proof?
Yeah.
All right. So we'll do the proof really quick. I won't bother writing what we're proving. I'll just start with line 1.
Okay.
1. Let M be parallel. Let's see. Try and keep the same order here. L parallel to M and M parallel to N. 2. Assume, by way of contradiction, that L is not parallel to N. If it's not parallel to N, then what does that mean?
Wait, intersection.
They don't.
Then L and N intersect at some point P. Capital P. Usually use capital in this class for points. 4. Then there are 2 lines through P parallel to M. Contradiction. Sorry, back and forth arrow. 5. Therefore, could have written that out better. Parallel to M, which contradicts postulate 6.1. I probably could have said. And then therefore we have L is parallel to N.
So it's like parallel, like if, sorry, parallel lines are kind of transitive. in that?
Yes.
Is the
Being
point-
parallel is a transitive property.
is the point.
If L is parallel to M and M is parallel to N, then L is parallel to N. So being parallel, it's transitive. You'll notice it's also reflexive, or symmetric, I mean. If L is parallel to M, then M is parallel to L. I don't know if we'd call it reflexive. Would we say a line is parallel to itself? We can't say that because a line intersects itself infinitely many times. So symmetric and transitive, yes, but not reflexive.
But it's not like an equivalent.
So it's not an equivalent relation since it's not reflexive.
Right.
Because a line isn't parallel to itself. Because how many times does this line intersect with this line? An infinite number, everywhere. So those 2 lines are not parallel.
They intersect a lot, yeah.
They intersect a lot. So not an equivalence relation, but it is transitive and it is symmetric. Good. Okay, next one.
Question real quick.
Oh, go ahead.
Is there a symbol for not parallel?
I don't think anyone would be confused if you did that. But maybe just make sure that one was smaller. I bet that notation is sometimes used. I don't know.
Used
I know I get too crazy with it.
in the book or
I have no clue if the book uses it. You guys have read this book a lot more recently than I have, right? You guys are reading it every night. I read this years ago. So maybe it's used in there, maybe it's not. I don't know. I wouldn't be surprised if that notation's used. I wouldn't be surprised if it wasn't used. Okay. Next proof. Just as simple. Maybe let you guys talk me through this one.
Okay.
So it's going to be a similar type of proof. We're going to get a contradiction. It's going to contradict the postulate. So proof by contradiction, big hint there. Let's see if we can do this one. Can't remember what it says. I just remember I did it by contradiction. If L is parallel to M and N intersects L at P, then N intersects M. Okay. So let's see. What were my parallel lines? L and M. So I've got L here. I've got M here. And I've got N N for sure goes through L. Does it continue on its merry way through M? And we know it intersects L at P. So, common notation for saying two lines are parallel, sorry. Okay, so I know that line's parallel to that line. I know N intersects L at P. I'm trying to prove N also intersects M. What would happen if N didn't intersect M? So let's pretend that it didn't intersect it. Whoop.
It creates another parallel line that goes through P.
Yeah.
And that's impossible.
Perfect. Then N is parallel to M if it doesn't intersect it. And so we have two lines through P parallel to M. Impossible.
Yep.
Oh, okay.
You see it?
Yeah, that makes sense.
All right. Need to see the proof on that, or you think you're good?
I'm good.
You good?
Yeah.
Okay. Bunch of definitions. Not going to write these things out. There's way too many of them. Just going to tell you what they are, and you're going to have to just get used to it. All right. First off, if I have a line L and a line M, so if I have two lines, and then another line intersects both of them, that new line we call a transversal. So N is a transversal to M and L. In our picture here, same thing. N was a transversal to M and L. It cut through both of them. It intersected both of them. We just call that transversal. Okay. Now, when we've got a transversal across two lines, then notice we create 8 angles. Right? Now, we call 1, 2, 7, and 8 exterior angles. They're the ones outside. We call 3, 4, 5, and 6 interior angles. They're the ones inside.
Like inside
Inside the parallel lines.
the parallel line.
Right? You got your, no, not necessarily parallel. We'll typically work with them when we're talking about parallel lines, but they don't have to be parallel. But inside the two lines right here, so here's our two lines. Inside the lines is this way, outside the lines is that way, is the way you think about it.
Does that have anything to do with the interior and exterior of an actual angle?
No.
No.
Just names of angles.
Okay.
So, when I have this transversal, 3, 4, 6, and 5 are interior angles. 1, 2, 7, and 8 are exterior angles. You with me? Now, you already know names for 1, 3, and 2, and 4. Those are vertical angles. 2 and 4, those are vertical angles. 1 and 3, those are vertical. 6 and 8, vertical. 5 and 7, vertical. Okay, now notice that 5 and 1 here kind of take the same positions with each of the intersections. 1 kind of corresponds to 5.
Okay.
We call them corresponding angles. 2 corresponds to 6. 3 corresponds to 7. 4 corresponds to 8.
They're not the same unless they're parallel, right?
Right, we're going to show that when you have parallel lines, they're all congruent. That will be our next proofs.
So them being corresponding makes them congruent, or does
No,
what
they're
does
just corresponding angles.
They just correspond.
They just correspond to each other.
they just do?
They just do. It's just names.
I
To
see
talk
that.
about relationships that they have to each other. Where we're going with this is we're going to prove that when I have two parallel lines, then corresponding angles are going to be congruent is one of the things that we're going to prove. So we'll prove that corresponding angles like that and that are congruent. Or that this one would be congruent with this one. That this one would be congruent with this one. And that this one, 1, 2, 3, 4, would be congruent with this one. Corresponding angles. Okay, so those are corresponding angles. Now we have interior opposite angles. What are interior opposite angles? So they have to be on the interior. And then what's the angle opposite 5 on the interior? They call it 3. Well, 5, 6, we already have a name for that one. That's its supplement, so we don't need a name for that. So the opposite of 5 is going to be 3, the opposite of 6 is going to be 4. So 3 and 5 are opposite interior angles. 4 and 6 are opposite interior angles. And then 1 and 7 are opposite exterior angles. And 2 and 8 are opposite exterior angles. It's a mouthful. Lots of terminology for how angles are related to each other. You'll kind of get used to it just by using them.
Yeah.
And yeah, I was going to write the full-blown definition for what each of those are. Way too much. Good with those? Okay. So now, I think we're ready for our next theorem. Ooh, move my camera. Hopefully all that was on camera. We're good. try and keep it so I have my scribble space. All right. That keeps me in my scribble space. Okay. So now, our next theorem. Let L cut lines.
What do you mean by cut?
Intersect them. Let L be a transversal to L1 and L2.
Cut, is that like vocabulary that we use for?
Yep, just intersects both of them. It cuts them. All right, so L is intersecting lines L1 and L2. Good so far? We are going to prove that L1 is parallel to L2 if and only if their alternate interior angles are congruent. What am I going to be proving in my picture? My alternate interior angles. I'm going to be proving that this angle is congruent to this angle. Those are alternate interior angles. Now, as a corollary to this, one corollary, it would be that L1 is parallel to L2 if and only if not only their alternate interior angles, we could have also did if their corresponding angles are congruent. And we could have also did if and only if their alternate exterior angles are congruent. And the proof is almost identical in all three of these cases. So we're going to do the case where their alternate interior angles are congruent. The proof is almost the exact same as if their corresponding angles were congruent, which is almost the exact same thing as if their alternate exterior angles were congruent. If I did that was congruent to that. We're just going to do one of the three cases. I'm not sure if the author gives you any of the other two as homework. Maybe. It's a good homework problem. Okay. So, this is an if and only if proof. So how do you prove an if and only if proof?
You prove one side.
Prove both
and the other
implications.
side.
Right, I have to show that the first part implies the second part, and then I have to show that the second part implies the first part. And the arrow tells us which direction I'm going. So I'm pointing my arrow that way, so I'm saying I'm going to show the first part implies the second part. So I'm going to show that if L1 is parallel to L2, then their interior angles are congruent. The second part, I'll show if the interior angles are congruent, then L1 is parallel to L2. Make sense?
Yep.
Okay. So, let's start. Assume L1 is parallel to L2. And now I've got to do a bunch of labeling. I've got to do a bunch of labeling so I can talk about my interior angle here and its alternate interior angle here. And also need to be able to talk about the corresponding angle up here. So, get to label a bunch of points to give me my picture here. Here's how that labeled up goes. Let C on line L, look at the picture as I read it, D on L1, and E on L2, such that A is between B and C, so I have to pick C up there, so that A is between B and C. Remember, I started with points A and B, and now I'm dumping everything else out. So I picked C, such that A is between B and C, and I made it so that angle BAD, and angle ABE are alternate interiors. So that's how I label my points. With me so far? So we've labeled all the points A, B, C, D, and E in our picture so far. I still need to get my F and G. Right? Okay.
Did you forget your angle symbol for B and C?
You're saying up here?
Yeah.
No, I picked C on L such that A was between B and C. So just pick C somewhere up there. I don't want to accidentally be, well, I also just need to point it there because I also need to talk about the corresponding angle.
Right.
So I'm going to pick F now so that this angle corresponds to this angle. Okay. Let F such that DAF, so pick F such that A is between D and F, and let G be in the interior of angle ABE here, such that angle ABE is congruent to angle ACG. This is where we're drawing a picture. Let's put a pin in all this labeling for a second. Let me just do the picture really quick without any labeling. I'm going to lose you in all my labeling here. So let's go the first way. I'm going to start with just two parallel lines. And a line that intersects them. Right? I know that this line is parallel to this line. The crux of my proof is to prove that this angle is the same big as this angle. If I know that this angle is the same big as this angle, how big is this angle compared to this angle? How do I know? Vertical angles. So the crux of the proof is showing that this angle is the same big as that angle, right? Here's what I am going to do. I'm going to come up to this point and I'm going to construct my ray here. I know that there is some ray such that this angle is congruent to this angle. You with me?
Yeah.
And I'm going to show that that ray actually lies on this line.
Yeah. Okay.
And so that this angle is the full angle here. You with me?
Yeah.
How am I going to show that this ray falls on this line? So imagine the line now that goes through this ray. So now here's L1, here's L2. I'm not sure what I'm going to call it over there. Let's just call this L3 really quick. How does L3 compare with L2? I know that that angle is the same big as that angle.
It's parallel.
These two lines have to be parallel. How do I know that? What did we do back here on our first theorem? That's following this exact construction. We showed how to construct a parallel line. We made, if you do the ray, if you construct the ray here, and then take the line through it such that those two angles are congruent, that's how we got these parallel lines. So I get that from theorem 8.1. Is how I know L3 is parallel to L2. Now I have L1's parallel to L2 and L3 is parallel to L2. What do I know?
They're parallel to each other.
L1 and L3 must be the same line. So this angle is this angle.
Right.
And so that angle is congruent to that angle.
Yeah, it's like that picture doesn't. Okay, yeah.
Right, it's an impossible picture drawing L3 not on L1. L3 has to be on L1 as a point. Those have to be the same lines. You get the big picture?
Yeah.
Scribble it out one more time. It's not that tough of a proof, and this is, our last hard proof of the day. So let's wrap our heads around it. So we start out with two lines parallel to each other. L1, L2. Right? Pick some line that intersects them. We've got an angle down here. I'm trying to show that this angle up here is the same big. Construct an angle up here that is the same big as that angle using a ray. Construct that angle so it's the same big as that angle. Now, using the same thinking we did over here, when we construct a ray like that, the line through that ray gives us another parallel line, or gives us a parallel line. So that gives us L3. So this line has to be parallel to this line, but this line is already parallel to that line. Since they contain a common point, those two lines have to coincide. And so L1 is in fact equal to L3. And so if I want to draw my picture accurately, I'd have to draw L1 and L3 as the same line, which would mean that this angle is like that. So that angle is congruent to that angle. And its vertical angle then is obviously congruent to it. Think you see it?
Yeah.
That's the thinking. Okay. So we reset up all of our labeling here. The last thing I did, I just barely picked this point G here. And I picked the point G such that, maybe use a dotted line so I don't make my picture too messy here. I picked G such that this angle is congruent to that angle. That's what we know so far. So here's the ray we chose that goes through some point G. I just picking a point G rather than a ray, then a point, simply so that we have a way to label the angle. With me so far?
Yeah.
So I know angle ABE is congruent to angle ACG. CAG. Sorry, that was probably confusing. CAG. Okay, we good so far? So we've chosen that ray, that point, that ray, such that that angle corresponds to that angle. The crux of my proof is to show that G actually lies on line L1. If G lies on line L1, then I have that angle is congruent to that angle, and then its vertical angle is congruent to that angle, and we're done. So from here on out, I'm trying to prove that G lies on line L1. Now I know that the line through AG is parallel to line L2 by theorem A1. So I know that this line through AG, whatever it is, must be parallel to L2 by our theorem over here. Not that the theorem tells us that, but by using the same construction that this theorem used. How do we construct our parallel line over here?
By having two congruent angles.
Well, the way we constructed it is we started out with, we had a line like that, and then we constructed the angle here congruent to this. When we do that angle construction, it gives us a line parallel to this line. That's how we constructed it.
Right.
We could re-go through the logic that if the line through AG wasn't parallel, then these two lines would have to intersect at some point C, then we get a triangle where an exterior angle was congruent to an opposite interior, and we could reinsert that logic. But we don't need to, because we already used that logic in our first theorem.
Right.
You with me? Kinda?
I see that that theorem says that it exists, but why can we assume that it just is the case, that it's parallel?
Okay. Let's say that AG is not parallel to L2.
Yep.
Then it has to eventually intersect L2, giving us a triangle. Look at this picture. So we have a scenario like this. Here's G. We'd have a scenario like this, right?
Yeah.
A, B, and G. These two lines then would have to intersect at some point C. And now this angle is exterior to triangle ABC, and it's congruent to one of its alternate interiors. Or one of its opposite interior angles.
Yeah, okay.
So we are doing the same construction that we did in theorem 8.1. So I shouldn't say by theorem 8.1, by maybe theorem 8.1 construction. We're following the exact same process constructing this line that we used in theorem 8.1. And theorem 8.1 gave us a parallel line. That's what I'm saying.
Okay.
Maybe it would have been easier to reinsert that logic in here. Probably should have done that. But you got it now?
Yeah.
Okay. Because if they didn't, you'd have an angle congruent to one of its opposite interior angles. Okay. So, by postulate 6.1, there's only one line through A parallel to L2. So, I know that this line is parallel to L2. I know that this line is parallel to L2. And there's only one line through A parallel to L2. So, this line and this line must be the same line. So, therefore, G must be in L2. L1. G must be in L1. G must lie somewhere on this line. So here is where G really is. It can't be up there. It has to be on the line. So then G is in L1, which means that angle CAG is the same thing as angle CAF. CAG and CAF are the exact same angle. Now I already knew that CAG was congruent to ABE by construction. That's how I constructed point G.
Yep.
So that we have right here. So I know angle CAG is equal to angle CAF, but I know that angle CAG is congruent to angle ABE.
So angle CAF is congruent to AB.
So, therefore, so doing it all in one go now. So now this angle, angle BAB, is congruent to what? What is BAD congruent to?
CAF.
It's congruent to CAF up here, right?
Yeah.
So angle ADB is congruent to CAF, and angle CAF we now know is congruent to ABE, which finally gives us that angle BAD is congruent to angle ABE. Or in other words, the alternate interior angles are congruent to each other.
Yes.
Now notice in that proof, we had to prove that corresponding angles were congruent to each other.
So let's basically give it to us.
So we already did the corresponding angles proof version as well, as we were doing this. The alternate exterior angles, it's basically the exact same proof, just starting with a different angle.
It's just starting with CAD, is what you're saying.
Well, let's imagine that we were trying to prove the alternate exterior angles were congruent. So I was trying to prove that this was congruent to this. Well, this is a supplement of that, and this is a supplement of that. And angles congruent to each other have their supplements congruent. Okay, so now we got that. Okay, so we went one direction. We showed that if L1 is parallel to L2, then their alternate interiors are congruent, their corresponding angles are congruent, and their alternate exterior angles are congruent. Now we need to go the reverse. We need to assume that their alternate interior angles are congruent, and show that means that the lines are parallel. You with me?
Yep.
And this direction is much easier. So assume that now, resetting up our picture, so try and scribble off a bunch of this. This is our point A. Hopefully it's not so scribbled that you can't see it. So resetting up our picture now. Now we're going to assume BAB is congruent to ABE. So assuming that our alternate interior angles are congruent to each other. You with me? Then I know CAF must be congruent to ABE. CAF must be congruent to ABE. How do I know that? If I know these two are congruent to each other,
Vertical
how do I know
angles.
these two are congruent to each other? Because these are vertical angles, so they're the same size.
Yeah.
So that's congruent to that, but that's congruent to that, so this is congruent to this.
Okay.
Okay. So, since angle CAF is congruent to angle ABE, CAF, ABE, well, then those are congruent to each other, and so their lines must be parallel to each other. How? By theorem 8.1's construction. How do you construct parallel lines? You construct an angle, and then an angle congruent to it, coming off the same line that bisects, that cuts through those two lines. So those two lines have to be parallel. Because that's exactly how you construct a parallel line. Make sense?
That's also by the construction of 8.1, not actually the theorem.
By theorem 8.1 construction. Good? Okay. Now, one easy theorem, and away we go. We're finally going to prove that the angle sum of any triangle is 180 degrees. I already showed you guys this, but show it to you again. This time I'll do it a slightly different way so that you're not bored.
All right.
Hate to bore you. Okay, so I need to prove that any triangle you give me, its angle sum is 180 degrees. Now while I fix this, one of you go up there and draw an ugly triangle. Draw an ugly triangle so that it would be hard for me to prove it for that triangle. Because we don't want to just show it for a nice triangle.
You can draw straight. Draw 89 degrees.
Try to keep your segments straight. Outside of that, I don't care what you do.
My best.
But give us an ugly triangle. Wherever you want.
The segments are straight and it's an ugly triangle.
Meaning, if we can't assume it's well behaved in any way, shape, or form. You know, we gotta prove it for any triangle. So, something ugly, not just some nice equilateral triangle, you know? We gotta prove it for any triangle. Okay, so we're gonna do it for this triangle here. One that's not so pretty. A, B, C. So, start it out. One, let triangle A, B, C be given. So we start out with any random triangle. Okay, how are we going to do this proof? We got to pick, let me move these points. We got to pick some part of the triangle to call the base. You know, we want to think about something as a base. It doesn't really matter how we think about it. I just got to start by putting a line through two of these points. I think the two that will keep the picture the most natural is through AC. But I could have done this line, and I could have done this line, and it wouldn't matter how we did it. So I'm going to pick AC. So here's some line through AC. We'll call it L1.
Question.
Yep.
Did you go through the definition of an angle sum?
Oh, no, we didn't. Where did I write that? I put it up here somewhere.
Right there.
It's right
to
there.
your left. Right after.
Oh, I skipped all those
Skip it.
definitions.
Yeah.
Sugar.
Yeah, I was gonna
That's
ask about that.
quite a bit of definitions.
That is quite a bit of definitions to skip. Doesn't matter. We'll go back to those after we finish the proof. You already have intuition for what we mean by the angle sum.
Okay.
So we'll rely on your intuition for now, and then we'll go back and be proper. We got the whole, yeah, we easily got the whole picture. Okay, so there's our line L1 through AC. Good?
Yep.
Now I know that there exists a parallel line through B. So we've got L2 here. Forgive the drawing. 3. Let L2 through B such that L1 is parallel to L2. Good? Okay. Now, look at this angle. Compare it to this angle. How do those two angles compare?
Let's see.
They're congruent. How do I know? They're alternate interior angles. And I know if two lines are parallel, then when you draw a line that intersects them, which AB does, then the alternate interior angles it creates are congruent. So, I need some way, let's see, I can talk about that angle. That's angle BAC. I don't have a way to talk about this angle yet. So I may just really quick label some points here. D we'll put here, and E we'll put over here. So let's really quick get D and E. 4. Let D and E on L2 such that DBE, and I'm not going to write the second part, but, and D is on the same side of E as A is of C, or D is on the same side of the line through EC as A. So in other words, D is the one over here, and E is the one over there.
Which is implied by the.
No.
It's understood from my picture, but I'd have to write that out, but I don't want to. Okay, so now, moving on to 5. Now I can talk about these angles. So now I know that angle DBA is congruent to what?
Angle BAC.
So then angle DBA is congruent to, say it again,
Angle
BAC.
BAC
You want to do the angle first.
by,
Oh, you did.
8-4.
yeah, by
Eight.
theorem 8-4. And maybe just note that they are interior opposites.
Isn't angle BAC just angle A?
Oh,
Sure.
by the way, can we use theorem 8-4 if they're corresponding and if they're alternate exteriors?
If that helps you keep track of it, we'll call that angle A. Sorry, say that again?
So, like in our proofs, can we use theorem 8-4 for corresponding and alternate exteriors?
Yes. Theorem 8-4 for corresponding alternate exteriors and alternate interiors. In fact, I don't even care if you never reference theorem for 8-4 again. You can just say this is congruent to this since they're alternate exterior angles. And go on your merry way, and everyone knows what you're talking about. It's very common to just say that, and everyone gets it. When the two lines are parallel, right? We have this as parallel to this.
Yeah, can we do that with a lot of things? Like, we can just be like, well, we know, like if we needed to look for the exact theorem or something, we could find
Yes, somehow quickly naming it. So I don't expect you to remember that the angle sum of a triangle is theorem 8-5. I expect you to know that the angle sum of a triangle is a straight angle. So you can say, since we know the angle sum of a triangle is a straight angle, da 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 da,
Okay.
or whatever. Okay, so there's our picture so far. So that's how I know that angle is as big as that angle. Now, this angle, how do we want to?
You want to do
You're gonna
angle
want another
BC.
point.
That angle is the same big as which angle?
CBE.
CB.
CBE, right?
Yes.
How do I know?
Opposite interiors.
Opposite.
Alternate interior angles.
Opposite, yeah.
Now I don't know. It's
Yeah.
alternate interior angles. I think before I told you guys opposite interior angles.
Yeah.
I know
That
it's
was
alternate.
wrong language.
It's all.
They're called alternate interior angles. I don't know why I said opposite.
That makes sense.
Alternate interior angles, alternate exterior angles, corresponding angles.
Okay.
Good?
Yeah.
Sorry. Okay. Anyway, so this angle is the same big as that angle because they're alternate interior angles. And I even wrote interior opposites. Oh my goodness.
So nice.
You guys have got to watch me better.
I don't know
They're
you're wrong.
alternate interiors. Right? You guys read the chapter, and so you remember it's fresh on your mind.
Yeah.
You're like, why is he talking about opposites? All I read about were alternates.
Oh yeah.
What is going on here?
Great meeting.
Yes. Okay. So we also have then angle EBC. EBC is congruent to angle C, and it's for the same reason stated above. They're alternate interior angles once again. You see it?
Are we going to do angle side angle? Is that what we're getting to?
No.
No.
Okay.
And now finally,
That's 6 rewind.
notice that angle B is congruent to angle B.
Right.
Correct. Angle B is congruent.
Right?
So that angle is congruent to a straight angle.
Then angle A plus angle B plus angle C is equal to, use some bad language here for a second, is equal to
This is equal to.
which angle?
DB.
Thank you. I really do not like that.
Okay, so then the sum of these three angles is congruent to, what was the first one? DBA
DBA. Oh, I see what it
plus angle B plus angle EBC, right?
is. No.
Well, in this case, that is equal to angle DBE, which is a
Straight angle.
straight angle. So, the angle sum of any triangle is equal to the straight angle.
How do we know for sure that angle DBA plus angle B plus angle EBC adds up to angle DB?
Because it starts with whatever this segment starts with. So the ray on our first angle to the ray on our last angle that we add together when you do an angle sum. So when I add up some angles,
Some angles.
if I were to add up all these angles, first off, to add them up, you have to draw them so that they're all adjacent to each other and share a vertex. And then when you do that, then the angle sum is from the first ray to the last ray. It's the two rays that are not shared by any of the angles.
Okay.
And so these are the two rays not shared by any of those three angles.
I see.
So that's what we mean by an angle sum. We're basically saying it now. Any other questions with that? Pretty simple proof, right? Just draw the two parallel lines. Notice alternate interiors. That's same as itself. Alternate interiors. Therefore, since that sums up to a straight angle, those three sum up
What
to a
about
straight angle.
Exterior angles of a triangle.
We could have used exteriors. The way I proved it to you last time was using exteriors. And I just extended the lines up, and I showed you it summed up to those three angles up there when you extended it up. Doesn't matter how you do it. So, lots of ways to do it. Here's one way to do it. Okay, let me give you all those definitions, and then we'll play with polygons.
Polygons.
Let me see what we can see. Maybe we can place polygons in the scratch space and don't have to bother messing with the camera again. Okay. Definitions. Angle sum. How do we sum up two angles? So if I'm trying to sum up this angle and this angle, first thing I do is I draw them adjacent to each other. Well, take one angle, draw an angle congruent to this one, adjacent to this one. So that's congruent to that. What's their angle sum? It's the angle you get of the rays of the sides not shared by the angles. So that ray and that ray. There's your angle sum. Okay. What are complementary angles? There's angles whose sum is a right angle. Supplementary angles, another way we can talk about now, they are angles whose sum is a straight angle. Okay. Simple polygon. You remember what a polygon was? We talked about polygon last time.
Yeah.
First we talked about a polygonal path. What's a polygonal path?
It's like the path that like a bunch of like
You just take a bunch of points
you have a bunch of points and then
and then connect them with segments.
such that the last.
That's a polygonal path. It's a polygon if the polygonal path starts and ends in the same place.
Yeah.
Okay, what is a simple polygon? In short, it's a polygon that doesn't intersect itself. Now, it's a polygon such that none of the edges intersect any of the other edges at points other than the vertices. That's a simple polygon. So, here's a simple polygon. Here's a not so simple polygon. You draw stars, not a simple polygon. You draw the pentagon, simple polygon. Is that all you did for? No, I didn't. Okay.
It says, you said that doesn't intersect on the vertices, so if you were to create a vertice on the line, what would it do? Would it be simple, right?
If I were to create the vertices on the line, no, it would not be simple.
Okay.
No.
So it's a simple polygon if the segments, because if you create that vertice on one of the lines, then you get it intersecting that point on the line which wasn't a vertice. So if I understand what you're saying, you're thinking of something like this, right? Am I guessing your question correctly?
Yes.
So that vertice intersects this side at a point that wasn't a vertice.
And what if that was a vertice?
Well, then,
Okay, and now you made me realize I missed the second part, and all the vertices are distinct. So you can't have two vertices in the same spot.
Yeah, I'm saying what if you were like to, oh, yeah. Okay.
Okay, but the intuition for it is, what's a simple polygon? It's one that doesn't intersect itself. Okay, adjacent vertices. So once I've got some polygon, adjacent vertices are just vertices that share a side. So this vertice is adjacent to this vertice. This vertice is not adjacent to this vertice. Adjacent vertices share a side. Consecutive angles. Consecutive angles are angles whose vertices are adjacent vertices. This angle is adjacent to this angle. This angle is not adjacent to that angle. What's next? A diagonal. A diagonal is any segment that connects two non-adjacent vertices. So not connecting those two, those are adjacent vertices. But connecting those two, that is a diagonal. It connects two non-adjacent vertices. How many diagonals can I draw from this vertice on this shape?
3. Not 2.
2. Just the one there and the one there. Those are the only two diagonals I can draw. Okay. A convex polygon. What is a convex polygon? A convex polygon is a polygon such that if you were to pick any 2 points on the polygon, that segment would not intersect the polygon. Almost. Let's say it a little bit more precise. Let me give you a picture of a non-convex polygon. First off, a convex polygon is a simple polygon with an extra condition. So it's a simple polygon such that pick any 2 points A, B, not on the same side. So here's a point A, here's a point B. pick any 2 points A, B, not on the same side. If the segment AB intersects the polygon, it is not convex.
Gotcha.
If it doesn't intersect the polygon, it is convex. Here's an example of a convex polygon. Pick any 2 points A, B you want, not on the same side. Their segment will never intersect one of the sides of the polygon. If my A is here, my B is here, nope, doesn't do it. If my A is here, my B is here, nope, doesn't do it. If my A is here, my B is here, nope, doesn't do it. So convex polygons somehow bend in on themselves, or the ones that aren't convex. Convex, it's somehow saying the angles are behaving nicely. We don't have it jetting into itself and back out. So not convex, convex. Good? An equilateral polygon is one where all of its side lengths are the same long. An equal angular polygon is one where all the angles are congruent to each other. A regular polygon is equilateral and equal angular.
Can you have a
So
If it's regular, if it's just equal.
question?
regular means equilateral and equal angular.
Can you have an equilateral polygon that is not equiangular?
Yes, very easily. If I drew that, so that's the same long as that's the same, that's equilateral, but this angle and this angle are very different sizes.
Can you have an equiangular polygon that is not equilateral?
Can I have it equal? Yes. Rectangle. Equal angular, not equilateral. All the angles are 90 degrees, but the side lengths are different.
Here. Okay.
Good?
Yep.
Okay? And then names of all the different polygons. What is a 3-sided polygon called?
Triangle.
A triangle. What's a 4-sided polygon called?
Quadrilateral.
Quadrilateral. What's a 5-sided polygon called? Pentagon. And then hexagon. And then
Septagon.
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 Right?
hept.
Hex.
Oh, that's right.
Hept.
Yeah, heptagon.
Heptagon is 7. And then what's 8? Octagon is 8. What's 9?
That's a hectagon, isn't it?
What?
That's a hectagon.
Nonagon. N-O-N. Non. Non for 9. And then 10-sided is
Decigon. Decigon doesn't sound right.
decagon.
Decagon.
We call it a decagon.
Yeah.
And back before Julius and Augustus messed with our calendar, we had September was the 7th month, and October was the 8th month, and November was the 9th month, and December was the 10th month. So, where some of the months ultimately get their names, same kind of naming, shows up in lots of places. You ever take organic chemistry, similar naming convention, after 4, I think. For 1, 2, and 3, they do use different ones.
Yeah.
Meth, F, crop,
I like that.
tetra, and then after that they follow the same one.
What about like the dice?
Hmm?
I don't have any.
Died?
Yeah, where do they get their names? Like dodecahedron and stuff like that.
My bad.
So the ones with regular faces get their names from the Greeks ultimately, because going all the way back, it's a proof, I think, going all the way back to the Pythagoreans, that there's only 5 regular solids. And it's not a hard proof to do, but we won't bother doing it right now. Let's see, what else do we need to talk about? So they got the names. Oh, so our last thing. We want to just observe some stuff. Nothing with the proof. We're just going to observe some interesting phenomena about regular polygons. We're going to look at some regular polygons. We're going to look at the sum of their interior angles and the sum of their exterior angles. So N here is going to be how many sides we're looking at. And then I'll do INT for the sum of their interior angles. And then EXT for the sum of their exterior angles.
Really? I like where that at.
Now, let's start out with a triangle, right? The simplest regular polygon we can make is 3-sided. You can't do a 2-sided polygon.
Right.
And have it be regular. So, 3-sided triangle. What is the angle sum of a triangle? If I add that angle, and that angle, what do I get?
A straight angle.
1 straight angle. We'll count in terms of straight angles. So I'm going to say 1s for 1 straight angle. You with me?
Yeah.
Now, let's think about it for a square.
You get
Straight angles.
For a four-sided polygon.
You get two straight angles.
Two straight angles. How do you know?
Because there's four
there's
90-degree angles. Or
two-
four half
There's two
angles.
triangles in a square.
So I said regular, but I didn't mean regular. I meant convex polygons. So our triangle could have been like that. Our four-sided figure can look like this.
Oh.
So what is the angle sum of any four-sided convex polygon?
It's two straight angles.
Two straight angles. How do you get that?
Because no matter
You can
what
still draw
four-sided
two
shape you
triangles.
make,
You can draw two triangles. Draw one of the diagonals. And now look, this angle plus this portion of that angle plus this portion of that angle is one straight angle. And then this portion of that angle plus this portion of that angle plus this angle is
Straight angle.
one straight angle for a total of
Two straight angles.
two straight angles when it was four-sided.
Okay.
You see it?
Any
Yeah.
other shape.
Let's look at a five-sided one and see what we get. So some five-sided shape, again, convex, but not necessarily regular. Let's see some of its interior angles. Three straight angles. How can you see that?
but that,
We can quickly cut this up into three triangles. The angle sum of all these angles, is one straight angle. That plus that is one straight angle. That plus that is one straight angle.
Yeah.
So you take this whole thing, plus this whole thing, plus this whole thing, plus this whole thing, plus this whole thing, you get three straight angles.
Does it just keep going up like that? So it's like 4 for 6?
Yeah, because every time we introduce, imagine I just add on to this now. So I come now and I'm going to add
One more point.
another,
vertice.
having how much I scribble on this isn't going to make the adding process very quicker. Let me restart and then add on. So we already did it for five-sided, right? Now I'm going to convert this to a six-sided polygon. How can I do that? I need to get rid, and let's quickly draw the triangles that this has. So here's the triangles that it has so far, right?
Okay.
Now, if I were to add a side, that means I got to erase one and split it into two.
Yeah.
And so now I need to make it something like this, right?
Yeah.
That's too close. But now, if I did that correctly, now we can add another triangle.
And you can always add one more
Because,
triangle as
yeah,
well,
what
so
we
that's
basically
side.
did is that side was already there, and then we just added the new triangle like that. And now I can come to this side and add the new, well, do it in a nice way. I
Do it
drew
in
my
the
finger
bottom.
so it's not working nicely. Well, our new triangle angle like that, so you can't see this clearly. But we could split into two triangles if we did do that. So we could do that. It's just not going to reuse the same line. I'm trying to show it so that we're always reusing the same line, building it out. But
Mostly from the same place.
I didn't build that very well. But the point is, yes, every time we add a point, we add a new triangle. And so every time we add a vertice, then we get another side length. And so in general, if I gave you some n-sided convex polygon, what's the angle sum of its interior angles?
N minus 2s.
N minus 2s. Can you see that?
Yeah. What's the angle sum of a circle? Or
360 degrees.
With it.
Okay.
That makes no sense.
I see what you're thinking is, because one way that we naturally like to think about a circle is an infinite-sided polygon,
Yeah.
right?
Yeah.
And so when we talk about the angle of a circle, well, we'll have to get into conversations about angles of a circle later. But there isn't a way to talk about summing up the angles like that of a circle.
You can't.
Is it because the line is curved? Is that what you're...
Because an angle, you need the rays, and you don't have the rays.
You can't talk about like an infinite sum of triangles, their angles.
We will introduce limits in this class. But we will have a lot to say about circles when we get to limits. Because we'll need limits to talk about them.
We're introducing limits in this class.
Yes.
What?
You have to use limits to talk about areas. What is the definition of an area?
Okay. Okay, that makes sense.
You define it in terms of an integral.
Right.
And so, yeah, we'll probably be talking about integrals. Well, no, we'll do integrals and calculus first, but I don't know. Might be pretty close. Will we get to integrals first in this class or in calculus? I don't know. But we won't talk about them as integrals here. But we will give full-fledged definition of a limit, and we'll use the correct one, not the calculus one.
Oh, I get it.
We'll actually give the proper one.
Awesome.
Anyways, that's jumping ahead. Last thing we want to notice now is talk about the sum of the exterior angles. So once again, let's say I've got some triangle here. And I want to add up the sum of its exterior angles. What do I mean by that? So imagine we extend this line out, and we talk about that angle. We extend this line out, and we talk about that angle. And we extend this line out, and we talk about that angle. So it's 3 exterior angles.
Okay.
What does this plus this plus this add up to?
270? Sorry, one sec.
Should be 360.
It should be 360 or shouldn't it?
So 2 straight angles.
Well, no.
How do we see that?
Because
What is this angle plus this angle?
It's
180.
180. Yeah.
One straight angle. What's this angle plus this angle?
1 straight angle.
What's this angle plus this angle?
1 straight angle.
So far we have 3 straight angles. But we counted both the interior and the exterior. We wanted only the exterior. So subtract away the interior.
So you
What was the
subtract-
interior?
1 straight.
One straight angle. And so we were left with
2 straight
2
angles.
straight angles.
Okay.
Let's try it again for a 4-sided polygon. So this time it has 4 sides. Once again, we're going to do the same thing. Talk about adding up its exterior angles. You with me? Now, if we sum this whole thing, we get 1 straight angle, 2 straight angles, 3 straight angles, 4 straight angles.
Yep.
So we have 4 straight angles, but now we need to subtract the interior. What was the interior of a 4-sided polygon?
2 straight angles.
2 straight angles for a total of
2 straight angles.
2 straight angles. In general, what are we going to do? The 4 here corresponds to how many sides we had, right? If I repeated this process for a 6-sided figure, we would do 6s and then minus its interior. And the interior of 6 was 4s. And in general, we are saying start out with ns. We have n straight angles, n being however many sides there are. And now subtract away the interior, which was n minus 2s.
Yeah.
And what are you left with?
You're
N
like,
minus n plus 2s.
Right.
Yeah.
So we have ns, maybe write it out a little bit, see if I can write down here. Ns. We have s times n times a negative is negative ns. And then negative times a negative is
Positive.
positive 2s plus 2s. So we have ns minus ns plus 2s comes out to 2s. So it's just going to be 2s every time.
It's always 2s?
Always 2s. Amazing, huh?
that makes sense. Oh, that makes so much sense.
Cool?
Okay.
Wait, I want
So just a fact to notice. Yeah, you can quickly play with that yourself. And that's it for chapter 8.
When are we going to get into tiling the plane with these regular polygons?
No.
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 No, you don't get a per the hex. That's the best tones.
Anything else? Okay, there's chapter 8. Enjoy your homework. Enjoy studying for your test. Test when you come back. Enjoy your holiday break.
What if we just finish the geometry book?